Welcome to the Antonio Zamora podcast that discusses a variety of scientific topics. Sand rims of the Carolina Bays. This video examines the mechanism by which the Carolina Bays developed white sand rims. Experiments suggest that rainfall percolating for many centuries through the soil of the elevated rims strained out the clay, leaving only the white sand. In the 1930s, the first aerial surveys of the Atlantic seaboard identified elliptical depressions with white sand rims, all oriented toward the common point. These elliptical features are called Carolina Bays, and they are easily observed in satellite images available in Google Earth. In 2014, I visited several Carolina Bays to examine their rims. The soil is basically pure sand like you can find on a beach. A small test hole about 20 centimeters deep showed that underneath the 2 centimeter white sand layer, there is a 5 centimeter layer of dark sandy soil with organic matter, followed by a deeper layer of sand. The soil does not have any cohesion and does not form clumps. In 2019, deep excavation of the rim of Arabia Bay in North Carolina demonstrated that the rims of Carolina Bays consist of permeable sandy soil through which water filters rapidly. Some Carolina Bays are on land that has been developed for farming, and their outline can be seen in aerial maps as ghost bays. Driving through North and South Carolina, you can identify ghost Carolina Bays by the contrast of the darker soil inside the bay and the white sand of the rim. The darker soil originated from organic matter that accumulated in the bays before they were drained for development. This LiDAR image with 20 times vertical exaggeration shows the clear outline of the same ghost Carolina Bay. LiDAR is a laser-based imaging technology that is very important for the study of the Carolina Bays because it reveals details that cannot be seen with aerial images. Carolina Bays have a mathematically elliptical shape. The geometry provides a clue about their mechanism of formation. In 1942, Douglas Johnson proposed that the Carolina Bays formed by a complex process starting from Artesian springs and wave action. He envisioned that the rims were formed by sand blown from the bay by the prevailing winds. This Aeolian hypothesis of rim formation was questioned soon after his proposal because the Carolina Bays are known to be thickly covered with vegetation, and it is virtually impossible for the wind to pick up much sand to transport it. In 2017, the glacier ice impact hypothesis proposed that the Carolina Bays and the Nebraska rainwater basins were made by secondary impacts of glacier ice ejected by a meteorite impact on the Laurentide ice sheet approximately 12,900 years ago. The impacts of the ejected ice chunks with energies of 13 kilotons to 3 megatons liquefied on consolidated ground, and the ice projectiles created conical cavities inclined at about 35 degrees that were remodeled into shallow elliptical bays by viscous relaxation. The extraterrestrial impact and the saturation bombardment by the glacier ice boulders caused an extinction event and a global winter. The date of the extraterrestrial impact is deduced from the disappearance of the North American megafauna and the onset of the Younger Dryas cooling event. The impact hypothesis explains the elliptical shape of the Carolina Bays and the origin of their rims. Carolina Bays are elliptical conic sections that originated as inclined conical cavities. An inclined conical cavity looks like an ellipse when viewed from above, as shown in this experimental impact on a sand and clay target. Raised rims are a typical characteristic of impact craters because impact cratering displaces material laterally by horizontal compressive forces and ejects debris ballistically to create stratigraphically uplifted rims. The Aeolian hypothesis cannot explain the precise mathematical shape of the Carolina Bays. The coastal plain soil varies in composition. The texture of the soil is determined by its amount of clay. Since many coastal subsoils contain 18 to 35% clay, these are further divided into depth of subsurface layer of more than 40 inches, 20 to 40 inches, and less than 20 inches. The major difference between sand, silt, and clay is the particle size. Clay particles are at least 25 times smaller than sand grains. In addition, clay minerals are characterized by their structure as two-dimensional sheets that tend to form layers impervious to water. From the impact experiments, it is clear that raised rims are formed around an impact cavity by compressive forces, but it is necessary to determine if the clay in the soil of the elevated rims could have been strained out by rainfall over many centuries, leaving only the sand and the white rims. I decided to test this hypothesis by making ice impacts on a viscous target of sand and clay in a container with good drainage and then spraying the surface every day with water to see if the clay and the sand separated. I fired a piece of ice against the sand and clay target using a slingshot. After the impact, I shook the container to speed up viscous relaxation. The second shot landed adjacent to the first impact, and the rim of the cavity slightly overlapped the first crater, similar to many examples in the Carolina Bays. Shaking the container speeded up viscous relaxation and decreased the depth of the cavity. I started a daily ritual of spraying the surface with water to simulate rain over the Carolina Bays. 30 days later, a forest of algae was growing on the surface of the container, and the rims of the impacts had a grainy appearance from the sand because some of the clay was being washed away by the daily spraying. The process was working, but it was evident that much time would be required to rinse out the clay from the sand. I wanted a proof-of-concept experiment that could be carried out more quickly. I cut some holes in a plastic container that could fit a coffee filter, and I made a holder for the container from a wire coat hanger. I put a sample of the sandy target material in the cup lined with the coffee filter. This was my first attempt at separating the sand from the clay. The first experiment with the coffee filter did not work very well. There were several problems. First of all, the coffee filter was very flimsy and it did not stand up to the spray of the water from the hose. Several times I had to stop to put the filter back in place to continue soaking the sand. As the flow of water continued, the water that drained from the experiment was cloudy with clay. When the container was half full of water, I stopped spraying and waited for the water level to go down. The water that dripped from the container became less turbid and the level of the water did not decrease significantly. This meant that the clay particles had clogged the pores of the coffee filter, making it impossible to separate the sand from the clay. I repeated the experiment with a piece of cloth instead of the coffee filter. This time, I secured the cloth to the container with some clips. The results were the same as with the coffee filter. Initially, some clay filtered out, but then the weave of the cloth became clogged and stopped draining. They say that the third time's a charm. Repeating the experiment with a cheesecloth filter worked very well. Right at the outset, you could see that the water flowing through the cheesecloth was very turbid with clay. In a few minutes, the sand was separated from the clay. Persistence pays off when testing an idea. You have to learn from your failures to know what to avoid and then try something different in a constant quest for improvement. The wide mesh of the cheesecloth and the high flow rate of water made it possible to separate the clay from the sand. The previous experiments with finer filters trapped clay particles that made an impermeable layer and stopped the percolation of water through the sample. This image shows some green and red sand grains because colored sand was used in several previous experiments using the same clay and sand mixture. The experiments described here helped to characterize the conditions needed to separate clay from sand for the formation of the sandy rims of the Carolina Bays. It is necessary to have the rain that drains easily, substantial water flow, and a porous matrix that allows clay particles to migrate to the subsurface. The Carolina Bays have always posed a challenge for the Aeolian hypothesis because wind and water mechanisms cannot guarantee the formation of mathematically elliptical bays with raised rims. By contrast, the impact hypothesis and related experiments demonstrate that inclined conical cavities formed by impacts on a viscous surface produce shallow elliptical depressions with raised rims after viscous relaxation. The experiments presented in this video show that it is plausible that the percolation of rain through the elevated rims of the Carolina Bays can wash out the clay of the soil to leave a white, sandy surface on top. Coastal plain soils vary in their porosity and proportion of clay. Both of these factors can affect the formation of sandy rims. Thank you for listening to this podcast. Please visit the YouTube channel or the website for many other interesting topics.